This is the first pre-recorded lecture from Chapter 11, which talks about the similarities and differences between gases, liquids, and solids. And this particular lecture focuses on probably the most important variable that determines the phase of matter, and that is intermolecular forces. Very, very, very important topic. The first thing that you need to understand before we get launched off into the different phases of matter and how they can vary is to understand what an intermolecular force is. The abbreviation we'll use for that throughout chemistry is IMF. And an intermolecular force is the attraction between separate molecules, okay? Do not confuse that with an intramolecular force, which is actually a chemical bond. So if you have something like HCl, hydrochloric acid, that bond that holds the hydrogen and chlorine atoms together is not an intermolecular force, it's intra. And actually, the key variable that determines whether state of matter will be a gas, liquid, or solid is actually the distance between the particles. Now, hopefully you would be asking yourself, all right, fine, what determines how far apart the molecules are from each other? That is intermolecular forces. So another way to state this, the fundamental difference between states of matter is the strength of the intermolecular forces between the particles. So in a gas, the individual molecules are quite far apart, which means the IMF, the intermolecular forces, are weak. They're not pulling toward each other very strongly. On the other hand, the molecules in a solid are packed as tightly as they can be, and therefore the intermolecular forces are very strong, and it pulls the individual molecules close together. So here's a pictorial, kind of gives you all of the information in a nutshell. This might be a good page to either summarize in your notes or print out or something. All right, so we are talking about gases versus liquid versus solid, and the key properties that you need to be able to discuss for each of them. So a gas has weak intermolecular forces. The distance between the molecules in a gas is large. You've probably learned the properties off to the right in high school, maybe even middle school, but it's good to review them. A gas assumes the shape and volume of the container, has very low density, and the thing that's very unique about a gas, which is important to remember, is that it's the only state of matter that can be compressed or squished down into a smaller volume. A liquid, on the other hand, the intermolecular forces are of moderate strength. The distance between the molecules are moderate. They're actually quite close in a liquid. And let's see, the volume doesn't change in a liquid because a liquid is not compressible. You can't change the volume. But a liquid does change its shape depending on the container it's in. And that's because the molecules in a liquid, even though they're pretty close together, they can slide past one another. So liquids flow, and so depending on the shape that you pour them into, they can change their shape, just not their volume. And finally, a solid has very strong intermolecular forces. The distance between the molecules are very, very small, and the shape and the volume both of a solid are set. You can't change them. They're not compressible, and the density, that means how much matter is crammed into a certain volume, is very high for a solid. The next few slides are going to be a little redundant, but just to give you kind of spread out solid, liquid, and gas and some of the key points. So again, a solid has very closely packed molecules. They cannot move around each other, so a solid cannot flow. So they have a fixed volume and a fixed shape. A solid cannot be compressed. And one thing that is a new feature, which we'll talk about later on, I think chapter 12, is there are two types of solid. There's a crystalline solid, and those are the really pretty solids that you can see, like some rocks make crystals. You can see snow crystals. So those are very regularly arranged structures where there's a pattern to how the molecules arrange around each other. And then there's something called an amorphous solid. That would be like rubber tires or something. It's still a solid, but it's not a beautiful crystal with a set pattern. So here are some pictures of crystals. Yeah, I forgot to mention diamonds. Diamonds make beautiful crystals, obviously. And then the amorphous solids, a couple other examples would be glass and plastic. And while the molecules in a liquid are not compressible, just like they are not compressible in a solid, they do have a little bit of space between them. Not much, just enough for a liquid to have what we call flow properties, or you can pour a liquid. Because of these flow properties, a liquid can change shape, all right, depending on the container it's in, but it cannot change volume. And finally, our free spirits, gas molecules. Gas molecules effectively feel no intermolecular attraction to one another, so they're free spirits, they're independent of one another, they have total freedom of motion, and there's a ton of space in between the molecules. So a gas can be compressed quite easily. The shape and the volume of a gas are not set. Both of them can be changed. In order to be able to predict intermolecular forces, we need to understand what causes them. All intermolecular attractions, and in fact, all chemical bonds, but right now we're talking about intermolecular attractions and not bonds, are a result of electrostatic forces. That's a really important term to understand. Electrostatic forces is basically an interaction between any type of charged particles. It doesn't need to be a fully charged particle, but any type of molecule that has any charge distribution, whether it be full ions or partial charges, will feel electrostatic forces. So let me give you an example. Let's look at water. So the red represents the oxygen atom, the gray represent the hydrogen atoms, and hopefully you remember a little bit from 1211 that water is a polar molecule, and that oxygen, since it's more electronegative than hydrogen, has a partial negative charge on it. That little squiggle stands for partial. And the hydrogen atoms are somewhat electron deficient, so we say they have a partial positive charge. So there's a little bit of partial charge distribution in water molecules. Because of that, the partial positive charges on the hydrogen atoms are attracted to the partial negative charge on the oxygen of a different molecule. And so you end up with an intermolecular attraction between the hydrogen of one water molecule and the oxygen of another one. There are three types of intermolecular forces. These you have to have not only definition memorized, which isn't the most important part, but you need to really understand what each of these three are, and then be able to look at a molecule and predict which types of intermolecular forces it has. So take your time, make sure you understand these descriptions. The weakest of the three intermolecular forces is called London dispersion force. Those occur in all molecules, but in nonpolar molecules, okay, that's molecules that have not even partial charges, London dispersion forces are the only type of intermolecular attraction. So what gives a nonpolar molecule any type of attraction to each other? It turns out that even though you may have a nonpolar molecule and no partial or full charges, the electrons, the valence electrons, and all of the atoms that make up the molecule kind of float around, have a little bit of loose play, and every now and then they will tend to congregate just for a brief instant on one part of the molecule, creating just for that split instant in time a partial charge. And so for that split instant and the partial charge, those molecules will experience brief and very weak intermolecular forces called London dispersion forces. The medium strength of the three intermolecular forces is called dipole-dipole attractions. Those are only between polar molecules. So it's important that you remember what makes a polar molecule. You may have to review. We went over those at the end of Chem 1211. Any polar molecule will experience moderately strength dipole-dipole attractions. The strongest of the three intermolecular attractions is hydrogen bonding. I hate that they call it hydrogen bonding because it's not really a bond. Okay? I hate that they have the word bond in there. It is an intermolecular attraction. So please try to remember that hydrogen bonding is not a real bond. It is between separate molecules, just like dipole-dipole and London dispersion. So in order to have hydrogen bonding, there are two prerequisites that have to be made. One, the molecule must be polar, and two, the molecule must contain hydrogen atoms directly attached to either fluorine, oxygen, or nitrogen. I always used to tell my students hydrogen bonding is fun, F-O-N. All right, that's it for the descriptions. Let's look at visuals of each of them and then talk about the type of molecules that would experience them. London dispersion forces, the weakest ones, remember those are the temporary or instantaneous attractions. So you look at a molecule, let's pretend these are hydrogen atoms. And you can pretend you're looking at hydrogen molecules, actually totally nonpolar, any diatomics are nonpolar. But at one instant in time, you may have the electrons around these nonpolar molecules congregate on one side of the molecule rather than the other side. And for that brief instant, that side of the molecule would have a partial negative charge, and the other side would have a deficit of electron density. We'd say it has a partial positive charge. That instantaneous dipole would then cause other nearby molecules to experience the same shift in electron movement, and you'd end up having a very brief, weak intermolecular attraction called London dispersion force. Again, it's important to realize that London dispersion forces are present in all molecules, okay? But the reason they're associated with nonpolar molecules is because in nonpolar molecules, there are only London dispersion forces. Okay, nonpolar molecules cannot have dipole-dipole attraction or hydrogen bonding. So the ability of a molecule to experience London dispersion forces depends on a property that's called its polarizability. I hope you're either taking notes or making note cards. There are a lot of definitions in this chapter. And this chapter kind of sets the foundation for the rest of 1212. So it's important you understand it. So what does polarizability mean? I always think of polarizability as meaning kind of shiftability or mushability. So if you imagine a molecule with all the valence electrons kind of floating around on the outside, the more you can manipulate or the looser held those valence electrons are, the more polarizable they will be. And the more polarizable an electron cloud is, the valence electrons in a molecule are, the stronger the London dispersion attractions are. So let's talk for a minute about what kind of things make a molecule more polarizable. Excuse my horrible artistry skills, but let's compare fluorine to chlorine to, that's supposed to be an I, iodine. So they're all halogens, but fluorine being toward the top of the periodic table is the smallest, then chlorine, iodine's bigger. I left out bromine, but no worries. They all have the same number of valence electrons. They're in group 7A, so they have 7 valence electrons. But the main difference is the valence electron of fluorine are held much tighter. Okay, they are closer to the nucleus, and it's the effective nuclear charge. If you were in my 1211 class, it'll make sense. Hopefully you've been exposed to that. If not, you may want to look up effective nuclear charge. But the valence electrons of fluorine have a higher effective nuclear charge. They're held more tightly. Therefore, they are less polarizable. They're less likely to kind of be shifted and swayed around or affected by anything else. Let's look at iodine, which is quite large, and the valence electrons are out in a much higher energy level. They're very much farther away from the nucleus. So the electrons in iodine are quite loosely held because of their simple distance from the nucleus and lower effective nuclear charge. And because of that, they're very much more polarizable. So you can imagine you can kind of mess with the valence electrons of iodine much more easily than that of fluorine. As a matter of fact, the larger a molecule or atom becomes, I can't write on this anymore. The larger an atom or molecule becomes, the more polarizable its valence electrons are, and therefore the stronger the London dispersion forces are. So let's look in general. So molecular mass. So just think of molar mass. So along the x-axis, molar mass is increasing. The molecules or atoms are getting larger. You don't really need, it's not important to really know the identities here, so don't get distracted by that. And along the y-axis, you have boiling point. And so what is the relationship between the size or the molar mass of an atom or molecule and its boiling point? As molar mass goes up, boiling point goes up. So let's think about what that means. This could be an essay type question on an exam. So this is an important concept to understand. All right, so let's go back to comparing fluorine to iodine. We're going to look at diatomic fluorine, F2, and diatomic iodine, and my wonderful skills again. So here's one molecule of diatomic fluorine, one molecule of diatomic iodine. Iodine is a much larger atom, so I drew them larger. Let's now talk about the intermolecular attractions between two fluorine molecules or two iodine molecules. Intermolecular attractions are usually drawn with a dotted line to show that they're not really full bonds like you see between atoms within a molecule. So let's compare the intermolecular attraction between two fluorine molecules and two iodine molecules. Think about what we just learned with molecular weight and boiling point. We learned from the graph on the previous slide that as molar mass goes up, okay, boiling point goes up. That's important. It's an important trend to understand and know. So let's look at why that is. As the molar mass goes up, so iodine has a much higher molar mass than fluorine, which means it has stronger intermolecular forces. Why would stronger intermolecular forces mean higher boiling point? It's important to understand what happens when something boils, okay? When you boil fluorine or iodine or melt them, change their phase of matter, what you're doing is you are separating them from each other. You are not breaking any real bonds. You are separating, you're pulling them away from each other. You're loosening the intermolecular forces when you boil or melt okay? And if the intermolecular forces are stronger, as they are in iodine, that means it's going to take more energy to boil or to separate those intermolecular forces. And as a result, iodine has a higher boiling point. Fluorine has a lower boiling point simply because its molar mass is lower and the intermolecular attractions between fluorine molecules are lower. Another factor that affects the strength of the London dispersion forces are the shape of the molecule. So let's compare two molecules that have the same molecular formula. So they're both, let's see, C5H12. Those are the molecular formulas for both. But this one, and pentane, is what we call linear. It's stretched out like a snake. And this one, neopentane, is kind of in a cluster, almost like spherical shaped. So it turns out that linear, the more stretched out a molecule is, the higher the London dispersion forces, and therefore the higher the boiling point. Bulky, clunky things don't tend to interact with each other as well. They can't line up on top of each other, and therefore they have lower London dispersion attractions and therefore lower boiling points. So now the molar mass is most important. So you want to look at molar mass first. If you have two things that have the same molar mass, then you can look at their shape. All right, let's move on to dipole-dipole type of intermolecular attraction. That was the moderately strong type. And those dipole-dipole are only for molecules that are polar. So again, it's important that you understand what makes a polar molecule. You may have to review that from 1211. And so if you have a polar molecule, you have partial charges that are permanent. They're not temporary. They don't come and go. And so the partial negative charge of one of the molecules will be attracted to the partial positive end of another molecule. And these dotted lines, again, are the intermolecular attractions between the two. So now that we've talked about London dispersion forces, which occur only for, well, occur in all molecules, but nonpolar molecules only have London dispersion forces, let's compare London dispersion forces for a nonpolar molecule with dipole-dipole attractions or dispersion forces for, dipole-dipole, for a polar molecule. So polar molecules have dipole-dipole, therefore stronger attraction, therefore they should have a higher boiling point and a higher melting point. Let's make sure they do. Looking at a nonpolar molecule which only has London dispersion, you can see that the boiling point is a lot lower than for the polar molecule, as is the melting point. Now, I'm going to sound like a broken record, but CH2O, that's actually formaldehyde, is polar. Okay, the oxygen is more electronegative than the carbon, so you have permanent dipoles. And so it does have dipole-dipole, but as I said, all molecules also have London dispersion. So to be accurate, formaldehyde has both London dispersion and dipole-dipole intermolecular attractions. It's probably also important to point out, you may not remember this from 1211, that any molecule that has only carbon and hydrogen in it is always nonpolar. And that's because the electronegativities of the carbon atom and hydrogen atom are so close to each other, there's really doesn't end up being polar at all, no dipole. This graph just kind of shows you a cool correlation. So the more polar a molecule is, the stronger the dipole-dipole intermolecular attraction, dipole-dipole, and therefore the higher the boiling point. I'm hoping that trend is starting to make sense to you. How do we know if something is more polar than something else? Well, there's a property called dipole moment. Dipole moment measures polarity, and so if you're given a dipole moment, the higher that value is, the more polar the molecule is. So check this out. These are arranged in terms of polarity. Look at the boiling point. The one that's the most polar has the highest boiling point. The one that's the least polar has the lowest boiling point. So pretty strong correlation. Now we are on to hydrogen bonding. It's the third and the most strong type of intermolecular force, and it can only occur with a select chemical structure. So as I said before, it only occurs when a hydrogen atom is directly bonded to either a fluorine, oxygen, or nitrogen. So you have to have something in the structure that looks like this, okay? That bond has to be directly, okay, so not separated by any other atoms. So let's look at ammonia, which has a structure, it's NH3, but if we drew it out, it would look like this, right? So here is one ammonia molecule, and here is another one. They shouldn't have drawn the regular bonds dotted. That's confusing. So the intermolecular force is here. And again, because ammonia is a polar molecule and nitrogen is more electronegative, nitrogen has a partial negative charge, and hydrogens with lower electronegativity have a partial positive charge. Okay, so the partial negative charge of a nitrogen on one of the ammonia molecules is attracted to the partial positive charge on the hydrogen of a different molecule. You could have intermolecular attractions between different molecules also. So for example, with ammonia, if you mixed it together with water, H2O, they're both polar. They both have hydrogen atoms that are directly bonded to either a nitrogen or an oxygen. So they can hydrogen bond with each other. But again, always remember the electronegative atom on one molecule is what forms the intermolecular attraction with the electropositive end of another molecule. This graph does a fantastic job of showing the effect of hydrogen bonding. So let's see. Along the x-axis tells us the period we're in on the periodic table. So we're moving down on the periodic table, period 2, 3, 4. Periods are the rows, the horizontal rows. Okay, so as we go to higher periods, we're going to larger molecules or higher molar mass. Okay, and so let's follow just one of these lines. You have CH4, carbons in period 2, and then silicon tetrahydride, silicon's right below carbon in period 3, and you can keep going up. Then we have germanium and tin. Okay, they're all in the same vertical group, group 4, but they're going down. So since they're getting larger, you would expect their molar mass, their size, and therefore their boiling point to increase, and they do, okay? So boiling point goes up as molar mass goes up. No surprises there. However, now let's look at atoms that are capable of hydrogen bonding. Remember, hydrogen bonding is fun. So let's look at atoms that are attached directly to either nitrogen, fluorine, or oxygen. Okay. So if you look, let's just start with ammonia. Nitrogen is in group 2, row 2, period 2 in the periodic table. Right below nitrogen, we have phosphorus. So let's compare nitrogen and phosphorus. Phosphorus is larger, therefore the molar mass would be higher, and therefore you would expect boiling point to go up, right? What on earth has happened here? the boiling point of pH3 is way lower than the boiling point of NH3. That's backwards of what we learned for London dispersion forces. Why is that? Clearly, NH3 is a huge exception, and that's because NH3 can participate in hydrogen bonding. And because it's such an extremely strong intermolecular force, it trumps all other intermolecular forces and makes the boiling point very high. So where you would expect NH3 to have a boiling point way down here, that is not the case because it can hydrogen bond. CH4 is not capable of hydrogen bonding, so it follows that normal trend that as size gets larger, boiling point gets larger. And of course, the same thing for hydrogen fluoride or water, since they are all capable of hydrogen bonding, they all have extraordinarily high boiling points. Alrighty, we're close to being done. I know this is a long lecture. I try to keep them shorter, but intermolecular forces are very critical. All right, so this is the type of thing I expect you to be able to do after listening to this lecture, reading the chapters. And by the way, I strongly recommend you open your textbook and go through it also. So identify the type of intermolecular forces for each of the molecules I've shown you here. Okay, and then compare two molecules within a pair and tell me which one has the stronger force. So here's where it's critical that you review what you learned from chapter 1211. It should be, from chemistry 1211. So it should be chapter 10 in your textbook, either 9 or 10, predicting polarity of a molecule. And so if you were to draw, you need to be able to draw Lewis structures first. If you were to draw the Lewis structure of BF3, boron trifluoride, and boron tribromide, you would get structures that looked like this. And even though the boron-bromine bond is polar, boron and bromine have significantly different electronegativity, so the individual bonds are polar. However, if you remember from Chem 1211, if a molecule is symmetric, the dipoles, we say, cancel each other out, and there is no net polarity. So if you imagine that you're the boron in the middle and you have three people standing around you pulling on you with equal strength, you're not going to move, okay? And that's because they're symmetrically arranged around you. So both of these are nonpolar. What type of intermolecular forces do nonpolar molecules have? Think about that and then see if you can answer what type of forces they each have and which one would have a higher boiling point. And I don't think you need a tip when identifying the type of intermolecular forces and comparing the next two in B. So I would turn off the lecture at this point, see if you can kind of sort through what you would answer for these, even if you're way off base, and then I'll go over the answers in more detail in the next slide. Alrighty, so let's compare boron trifluoride and boron tribromide. Again, draw the Lewis structures first, so go back over those rules if you need to for how to do that. Boron is a moron. Boron is happy with only 6 valence electrons. It's one of the exceptions. All right, since both of these are symmetric, they are both nonpolar molecules. Therefore, the only intermolecular attraction they will experience are London dispersion forces. With London dispersion forces, the higher the molar mass, the stronger the attraction, and therefore the higher the boiling point. Okay, so which one of these has a higher molar mass? Well, bromine has a much higher molar mass than fluorine. So boron tribromide will have the higher molar mass and therefore a higher boiling point. I drew out the structure for the next two you're comparing, and the only difference is the group on the end. There's a chloride on the end of the top one and an OH on the bottom one. So not that you need to know these names. Once you get in organic chemistry, the top one will be called ethyl. That's an ethyl group, chloride. And the bottom one will be called ethyl alcohol. Ethyl alcohol is the stuff that's mixed with water to make alcoholic drinks. All right, so we're going to compare the intermolecular forces. The first thing you have to do is identify the type of force, okay? So what type of force would ethyl chloride experience? Well, they all have London dispersion forces, all molecules do. Then you have to ask yourself, is it polar? If it's polar, it would experience also dipole-dipole. Well, yeah, chlorine has a pretty high electronegativity that's different than carbon. So I would say there's a partial negative charge in chlorine, a partial positive in the carbon, but that's not even that important. It is polar, so it definitely has dipole-dipole. Now, can this molecule experience hydrogen bonding? And no, okay, it doesn't meet the prerequisites, so no hydrogen bonding. All right, let's look down. So that would be 1A. We'll call this 1B. All right. So again, all molecules experience London dispersion attraction. This is polar. You have oxygen, which has a significantly different electronegativity value than carbon or hydrogen, so you definitely have partial charges. So you have dipole-dipole. Now, can this participate in hydrogen bonding? Yes. You have a hydrogen atom directly bonded to an oxygen, so it can participate in hydrogen bonding. This molecule has all three intermolecular forces, and it has stronger attraction because of its hydrogen bonding than the other one. Therefore, you would expect the boiling point of ethyl alcohol to be higher than the boiling point of ethyl chloride. Just a side note here. We've been talking about separate molecules and how they interact with each other. It's important for you to understand that individual atoms have intermolecular attractions also. So let's say that I had a neutral sodium atom and a neutral boron atom. They're going to have some type of intermolecular attraction between them too. You're not going to run into that much, but I just want you to be aware of that. You can also, really any type of species are going to experience electrostatic or intermolecular attractions with each other, but a subset that's kind of important to understand is the attraction that occurs between ions and dipoles. And that's particularly important when you're talking about dissolving a solute in a solvent and making some type of solution, okay? So what is an ion? It's a charged particle. So, for example, chloride or sodium, those are both ions, okay? So let's say you have those, and let's say that you put them in water. Say you're dissolving salt in water. Okay, so not only are the two ions going to experience very strong attraction to each other, each ion will also be attracted to the polar water. And so those are called ion dipole forces. And those are actually stronger than the three regular intermolecular forces experienced between molecules. Here's a list of intermolecular attractions from weakest to strongest. So I would again either print this down or write it down. London dispersion forces are the weakest of all intermolecular attractions. Okay, they're present in all molecules, but they're the only type of attraction present in a nonpolar molecule. Remember that London dispersion increases with molar mass or size. All right, dipole-dipole intermolecular forces are the next stronger. You have to have a polar molecule, which means it can't be totally symmetric to have dipole-dipole. If your polar molecule has a hydrogen atom directly bonded to fluorine, oxygen, or nitrogen, you will have hydrogen bonding, okay, which is the strongest of the intermolecular attractions between neutral molecules, okay? But as just kind of a throw out, I used to leave this last one out, but then I saw it on the ACS final, so I wanted to throw it in. And that becomes important in Chapter 12 when we talk about solutions. So, ion dipole attractions, attractions between ionic ions, charged particles, and then a separate polar molecule. Ion dipole attractions are in fact stronger than hydrogen bonding simply because the ion has a fully developed charge, not a partial charge. And I guess if you want to carry that further, you could say there are ion-ion attractions, which are the strongest of all because both of them have a fully developed charge. So by far, the three intermolecular attractions between molecules, neutral molecules, are what I really want you to understand, but just kind of keep in mind the ion stuff. All right, so here's a chart I love just because it kind of summarizes key points of all of them. So you may want to take a minute, look that over, or jot it down. And then our last slide. Why do we care so darn much about intermolecular forces? They affect an incredible amount to do with molecules, a huge amount. Not only do they determine the state of matter a compound is, they determine the melting point and boiling point, the surface tension, which we haven't learned a lot about. They determine the viscosity and the solubility. I'm not going to go into depth with surface tension and viscosity, but I'm going to make sure you understand what viscosity is because I have seen that show up as a question also. Viscosity is really kind of how thick a liquid is. So you would say honey has a higher viscosity than, let's say, water. I think the textbook definition is resistance to flow. What makes a liquid have this higher viscosity or thickness about it? Well, strong intermolecular forces do. So the stronger the intermolecular force is between molecules, the higher the viscosity, okay? So whatever's in honey, it's making a really strong attraction between the honey molecules, stronger than there are between water, and that's why honey has such a high viscosity. That is it for the first lecture. And the next lecture is talking more about changing phases of matter and the thermodynamics, thermal chemistry that are involved in it.